Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the lecture 2 of module 7. In the lecture 2, we are going to learn about the shear wave splitting. Before we start the lecture today, we are going to also have the review of what we have learned in the previous lecture. And then we will be learning about anisotropy in the lithosphere and the asthenosphere. And finally, we will be having the summary of today's lecture. As far as the review of previous lecture concerned, we learned that any material in which there are more than two elastic constants are present can be considered as anisotropic material, and the maximum number of elastic constants for an anisotropic material reach up to 21. So all in all, more than 2, if it is, then it is an anisotropic material, and for an isotropic material the elastic constant will be 2, that is lambda and mu. Lambda is the Lami's parameter and the mu is the shear modulus. Then we learnt about minerals and the rocks comprises anisotropy either due to the lattice preferred orientation or shape preferred orientation. In short, they are known as LPO and SPO. Then we learnt about transverse isotropy, and it is often characterized by 3 parameters. Those are zeta and phi and neta. And if the material is isotropic, all these parameters will be equal to 1, and in case the structure is layered, then zeta will be greater than 1 and phi will be less than 1. Individual values of zeta, phi and netas are like this. Zeta is n by L, that is equal to S1 by S2 to the power square. Phi is equal to C by A, that is equal to P2 by P1 to the power square. Neta is equal to F upon A minus 2L. And in general, the P wave velocity varies with azimuth as P as a function of theta, that is equal to A1 plus A2 cos 2 theta plus A3 sin 2 theta plus A4 cos 4 theta plus A5 sin 4 theta. And in case of teleseismic studies, the 4 theta terms will be very small, so it can be ignored in those kind of studies. Then we learnt about magnitude of anisotropy, which basically calculates how much anisotropy is present due to a particular mineral. So magnitude of anisotropy is represented by a small letter k, that is equal to the maximum velocity minus the minimum velocity divided by the mean velocity. So in that context, we learnt that the most isotropic material that is present in the earth is garnet, and it has the magnitude of anisotropy, that is k, less than 1% for both P and S waves. Likewise, the most anisotropic material is sheet silicates like mica, for which the P and S wave velocities anisotropy is around more than 60% and 116% respectively. So today we are going to start the lecture by learning about the technique that is known as shear wave splitting. And it is a very important technique, and it has been used very widely, and it is very popular in the case if somebody want to study about the deformation and the mental flow in the asthenosphere. So the anisotropy within and beneath continental lithosphere is often studied with a technique that is known as shear wave splitting technique. So in this technique, what actually happens when SKS wave comes out of the outer core, then it comes out as a SV wave. When this SV wave encounters anisotropy, then it splits into its two components, that is along the fast axis direction and along the slow axis direction, and these components are respectively known as SH wave energy and SV wave energy, and then they keep on splitting, and whatever distance they travel in the anisotropic material, as per that they also involve the splitting time, and we try to study that splitting time and also the polarization angle using the technique of shear wave splitting. So in the cartoon that you are seeing over here, you can see there is a incoming shear wave that is represented by black color. As soon as it enters into the anisotropic material, then it gets splitted into its components for the fast axis and the slow axis, that are SH and SV wave energy. And then the fast velocity, the wave that with the fast velocity travels faster, that is in represented by blue color, and the wave that is in the red color travels with the slow velocity in comparison to the blue wave. So after encountering an anisotropic layer, the wave gets split onto the fast, or you can say quasi S1 wave, or slow wave, that is quasi S2 wave along the axis. And if we assume the transverse isotropy with a horizontal axis of symmetry, the two polarized waves travel at a different speeds and arrive at different times. Thus, if the signal SKS signal on the radial component in an isotropic earth is considered to be ST, then its projection on the fast axis, that is the S1T axis, and the slow axis, that is the S2T axis, will be given respectively as S1T is equal to ST cos phi and S2T is equal to ST minus delta T sin phi. So if you look at this particular diagram here, you can see there are the two axes. One is the S1 axis, that is the fast axis direction, and the S2 axis, that is the slow axis direction. Those are more or less orthogonal to each other, and the wave that is traveling along the fast axis will be the fast axis wave, or you can say the wave traveling along the fast direction, and the wave that is traveling along the slow axis, that is S2 wave, or it is represented as S2T. So if we consider the SKS signal, that is before entering into the anisotropic material, is represented as ST. So the S1T that is traveling along this direction, the fast axis direction, can be taken as the component of radial component, that is the ST component, and if we make the projection onto this particular direction, then it will become ST cos phi, and there is another component along this direction, that will be your ST minus delta T. Delta is T is for the delay time, because along this axis the wave is traveling slower with an amount of around delta T, and then we will have sin phi here. So that is what it is written here. S1T is equal to ST cos phi and S2T is equal to ST minus delta T sin phi, where phi is the polarization angle and delta T is the delay time between the fast and the slow polarization. And the typical values for delta T for upper mantle splitting are ranging from 0.5 to 3 seconds. If you want to understand everything in a short summary, then you just consider there is this particular uh, inner core and there is this outer core here, and we have a mantle here, and a S wave has started to go down from here. As soon as it enters into the outer core, then it gets the K component, and when it reaches to the boundary of the mantle and the outer core, then this radial component, or you can say this component K, gets converted into the SV wave here, SV wave, and if there is any anisotropy present here, then this SV wave will split into its component SH and SV wave, or along the fast axis direction or slow axis direction, that is ST, S1T and S2T, and then we will have to calculate this anisotropy, how much anisotropy is present into this particular area or the upper mantle, and then it will be recorded at the receiver. So now, since we have seen previously on the slide that S1T is equal to ST cos phi, S2T is equal to ST minus delta T sin phi, and most of the energy is basically in the form of SV wave, because when S wave travels towards the outer core and at as soon as it encounter outer core, then the component it has the SV wave, because SH wave energy will be reflected wave. So only energy that will be transmitting into the outer core will be the SV wave energy, that will be known as K wave energy. So that energy will mostly be concentrated on the radial component, and if suppose this is your radial component, should be R. So this is your radial component and all the energy is on the radial component, and as soon as it comes out of the outer core, then there will be conversion happen from K to SV wave, and that SV wave, if encounters anisotropy either in the D double prime layer at the base of the core mantle boundary or at the upper mantle, then it will be traveling into the two directions as a splitted component, that is the fast axis direction and also the slow axis direction. So that is what it is written here, K wave coming after the outer core, all energy is in the radial direction. After it enters anisotropy, as T gets distributed onto the fast and slow axis, the wave on the slow axis is delayed by delta T, that is the splitting time. And here this angle is phi, that is your polarization angle, and this polarization angle is represented by this letter phi, and there is another parameter delta T, that is splitting time. So now what we want to do, we want to record our seismogram, preferably on a seismometer in the RT coordinate system, where radial component will be recording the SV wave energy and the tangential components will be recording the SH wave energy. So in order to do so, what we are going to do, the energy that was splitted from SV wave as it enters into the anisotropic material, then after the splitting, it has the fast axis energy, that is represented by Ft, and the slow axis energy, that is represented by capital St. So that is along the fast axis direction, that is your Ft, and along the slow axis direction, that is your St, and we want to rotate it into the preferred seismometer coordinate system, that is the radial and the transverse coordinate system. So we want to have capital RT and TT, that is for the seismometer coordinate system. So RT is in this direction and TT is basically in this direction. So what we are going to do, we are going to take the projection of Ft and St along the RT coordinate system. So for RT, that will be equal to, along this direction, that will be equal to Ft cos phi, that will go there over. So Ft cos phi and minus St in this direction. So St sin phi here, and this St sin phi will be in the negative direction, so there will be negative here. And we know from the previous slide, Ft, that is S1t here, Ft is St cos phi. So we can incorporate there over here in place of Ft, then it will become St cos square phi. Thereafter that will become plus, because this is basically minus here. So that is minus St minus delta T sin phi. So we can incorporate St from there, that will become St minus delta T sin square phi. Similarly for Tt, we can write Ft cos phi, that is in this direction, and that is St cos phi, Ft cos phi, and this is St sin phi similarly. So when we add them together and writing the values of Ft and sin t from here and there, then you can get these values, and in terms of sin 2 phi, that can be written as St minus St minus delta t in bracket by 2, and there will be sin 2 phi. So what we normally not expect any SKF on the transverse component, but anisotropy yields a combination of both the fast and slow orientation on the both radial and the transverse component. So it will become something like this that we have just seen. So in the SKS splitting, or you can say in the shear wave splitting, what we generally do, we have the raw records where you have the radial component and the transverse component, and then you rotate these components. These are uncorrected SKS waves. If you want to rotate them along the fast and the slow axis direction using the polarization angle, and then what will happen? The SKS waves should look similar to each other, and then finally you will correct them by incorporating the splitting time. Then what you will observe, you are going to get the zero SH wave energy on the transverse component, and all the energy will be concentrated onto the radial component. So what we are trying to do, we are trying to find out a correct combination of the splitting time and the polarization angle, so that after the correction, all the energy should be in the radial direction, or you can say the particle motion should only be restricted to the radial direction, keeping the transverse component SH wave energy zero. That means the particle motion along the transverse direction will be having less energy in comparison to the high energy on the radial component. If you want to find that correct combination of the phi and delta t, then you will have to do it using the grid search technique, where we are trying to find out that combination of phi and delta t so that we can minimize the energy on the transverse component, and that will be done by the grid search method, where we are going to plot some contours in order to have that best combination of polarization angle and the delay time delta t. And then this particular bullseye will be representing the correct combination of polarization angle and the delay time. So if you will see the particle motion plot in the uncorrected SKS wave, you can see the particle motion is along the transverse direction, also is also along the radial direction. But in the corrected form, you can see all the particle motion is parallel to the radial direction. There is almost no energy in this direction or in this direction. So this is what we want to do. We want to find out that combination of polarization angle and the delay time, so that all the energy should be along the radial direction. And this is the concept of shear wave energy, that we do it in many ways. The typical values for the magnitude of shear wave splitting delay time range in between 0 to 2 seconds. There are some points that we must remember about the anisotropy in the lithosphere, asthenosphere. So horizontal sediment layer can create transverse isotropy of up to 15% with a vertical symmetry axis. Azimuthal anisotropy is thought to exist with a horizontal axis perpendicular to the dikes intruded in the upper crustal layers of vertical sheeted basaltic dikes. A primary source of anisotropy in the upper crust is the presence of the cracks that are oftenly sometimes called as joints, and often they are fluid filled. When these cracks occur in horizontal sediments that would by themselves have vertical axis transverse isotropy, the combined result can be orthorhombic symmetry. The lower continental crust tends to have strong sub-horizontal layering, perhaps resulting from ductile deformation, which causes seismic anisotropy. This is the example of subcrustal oceanic lithosphere that shows a strong azimuthal anisotropy. If you look at this spreading center where the new crust is forming in this directions, so the preferential direction of the orientations of the olivine crystal will be along the direction of the spreading, that means along the direction of the new crust that is forming, and that will be the direction of the fast axis of the olivine, that is preferentially the fast axis of the velocity in the spreading direction. And here in this particular plot, the variations of the Pn wave velocities near y are shown, and you can see the maximas are obtained over here. So that means you can see the velocity of Pn wave are varying with respect to azimuth here, and this is the change in the velocity, or you can say the P wave velocity anomaly. So velocities are not same in all the directions. The P wave velocities are maximum in this direction, that is around 90 degree and 270 degree, that is basically showing the direction of the fast velocities, and that is at 90 degree and 270 degree, that is for the azimuthal anisotropy, and that is in the direction of the spreading when the plate are formed. So seismic anisotropy within continent is thought to reflect crystal alignment created during a tectonic episode and then frozen in. The anisotropy is a result of last episode of tectonism which resets any previous anisotropy. For plate collision, the fast axis is usually subperpendicular to the principal stress axis or parallel to the resulting orogenic belts. There may be deeper anisotropy due to the orientation of the olivine in the flowing asthenosphere. However, it is sometimes difficult to distinguish this effect from lithospheric anisotropy. And this is the diagram which is taken from Saikia et al. 2010, and where they have used the shear wave splitting technique to see the asthenospheric flow in the mantle, and in this particular diagram you can see most of the fast axis azimuths tend to be aligned along the northeast or the north south directions, and that is basically close to the absolute plate motion direction of the Indian plate. Indian plate is basically going in this direction and subducting beneath the Eurasian plate that follow the trend of in the northeast north south direction. And this diagram, if you look at this, represents the anisotropy in the Pacific Ocean that is derived by the parameter zeta as a function of age and depth. And if you look at this diagram and all these curves that are basically represented for the the time scale in between 0 to 4 million years, and what you can see, there is a curve for the 0 to 4 million years, 4 to 20 million years, 20 to 50 million years, and there is 52 to 110 million years and 110 plus million years. When this particular parameter gets greater than 1, then you can see the this is the value where the zeta is equal to 1. If it goes more than 1, then the love wave velocity becomes greater than Rayleigh wave velocity, and when it becomes less than 1, then the Rayleigh wave velocity becomes greater than the love wave velocity, and when the zeta is greater than 1, then it indicates horizontal mantle flow. When there is zeta less than 1, then it indicates vertical mantle flow. Here you can see the splitting of a diffracted S wave which presents the evidence for anisotropy at the base of the mantle for a South American earthquake recorded at a Canadian station. So you can clearly see there is a difference in the arrival time of SV and the SH wave, which basically indicates towards the difference in the velocities, and hence suggesting transverse isotropy in the South American earthquake that has recorded at the Canadian station. So the summary is going like this. As shear waves travels across the mantle and truss, they can split when traveling through anisotropic media that serve the basis of the shear wave splitting. To study the lithospheric anisotropy, we would normally not expect any escapes on the transverse component in case of isotropy, but anisotropy yield a combination of both the fast and the slow polarization on both the radial and the transverse component given by RT, TT, that is RT is equal to ST, that is the value of energy that is for the shear wave before it comes in the mantle, and that is the SV wave energy in the outer core, and that is the ST cos square phi plus ST minus delta T sin square phi, and TT is equal to ST minus ST day minus delta T divided by 2 sin 2 phi. Source of anisotropy in the upper crust is the presence of fluid filled cracks, horizontal sediment layers, intruded dikes, preferred orientation of olivine crystals yielded by spreading process. So that is all for today, and we are going to meet in the lecture 3 for module 7, and thank you so much. Bye bye.